Hello, and welcome to our first colloquium of Quantum Information Science and Technology Initiative that is funded by the College of Engineering's Next Level Ideas. As our college is very interested in growing quantum information science and education at UC Davis. And so this quarter, we have a really interesting lineup of speakers, both locally from the 4 departments at UC Davis that are quite involved with the quantum information, that being math, physics, PCE, and computer science, as well as world-renowned visiting speakers who will be joining us throughout the quarter. So here's our lineup. If you're interested in learning more about quantum information, science, and technology at UC Davis, this website, quist.ucdavis.edu, has all details on research, coursework, student organizations, and more. Now, I would like to thank a few people for making this happen. First and foremost, Isaac Kim, who worked tirelessly to bring some of these speakers in, as well as Margie on the ground, who made the course possible so that you guys can also get credit for attending these interesting talks. And now I'd like to give the floor to Isaac.
Okay. Great. Thanks, everyone. Let me first point out that Marina actually did 99% of the job. I didn't really do much, so you got to thank her. And first about the logistics, so we have a attendance sheet. Some of you are maybe just auditing. In that case, it's fine. But if you are taking this course for credit, there is an attendance sheet moving around. So please write down your name and department. Okay. And with that, I think I'm ready to introduce today's speaker, Bruno Nachtergaele. And before I give you the official bio, let me give you like a short introduction of him, how I know his work. So he's done like many foundational works in mathematical physics and quantum information. So many of his papers are like the go-to classics that you read when you're in like grad school. And I did read many of his papers when I was in grad school, which were very foundational and still very important. And currently, he's a distinguished professor of mathematics at UC Davis. His general research area is mathematical physics with an emphasis on equilibrium and non-equilibrium statistical mechanics, quantum spin systems, quantum information theory, and applications of these fields in condensed matter physics. So Bruno received his PhD in theoretical physics from University of Leuven, Belgium in 1987. And he held positions at the University of Chile and Princeton University, and visiting positions at the Newton Institute, the University of Marseille, CNRS, basically many places. So he is a member of the American Physical Society and the International Association of Mathematical Physics, of which he currently serves as the president. He's also a fellow of the American Mathematical Society and the American Association for the Advancement of Science. And he was invited as speaker at the International Congress of Mathematicians at Beijing in 2002, which is a big deal. He received the Humboldt Foundation's Carl Friedrich von Siemens Research Award, forgive me for my pronunciation, and was elected to the Academia Chileana de, I can't possibly pronounce this, but I think you get the gist of the idea. So Bruno is a very accomplished researcher in the field of quantum information and mathematical physics. We're very happy to open this course, starting with him. So I'll invite Bruno to come over to the podium.
Thank you, Isaac.
So let's end that.
And Marina for organizing all this, making this possible. I'm really excited that you're starting such a series on our campus. And so
I think I know how to do this, but
I'm going to talk about mathematical approaches of quantum states. And don't worry, it's not a mathematics colloquium, but it is a colloquium about mathematics. it is colloquium, but of course, quantum information. And we're almost there. Thank you, Isaac. And of course, so as I said, I've worked in this field for a number of years, and I will mention these also many people, also collaborators. I thought about starting to list them, but it didn't seem quite right. It would be a long list, and then maybe I forgot someone anyway. So I'm certainly not implying that I know this work by myself. Now, we seem to have lost the connection here. Okay, here we go. So I have a list of topics, and it seems like a long list. There's lots to talk about. In fact, there's a 9 item that says further topics, so there's lots more to talk about. But what I would like to do is to show you that these are kind of related. And it's about quantum states, the issue of entanglement, error loss, complexity of states, what happens if you look at ground states. And I will talk about matrix product states and some examples of Hamiltonians of which the ground states are matrix product states, and then go to the Torrey-Code model, which is a 2-dimensional model for which a tensor network state is the exact ground state. And then at the end, I will mention a recent result that I think is quite interesting. Okay, so, well, here on this slide, not very much I have anything new for you, but just to get started, we're going to be talking about quantum systems that, say, are n qubits. The Hilbert space is finite dimensional. It has a tensor product structure. Here it is. And we all know that if you have a unit vector in the Hilbert space, you can define a vector state of the system. And we can denote it in different ways. And in the literature, definitely you find several notations for it, depending on what community or what people want to emphasize. So it's a vector psi in the Hilbert space. It's an expectation functional that is defined by psi. In some parts of the literature, where people also discuss infinite systems, these expectation functionals are often denoted by omega. Or we can emphasize that the state is related to a density matrix by making this notation here rho psi. So in all cases, it refers to that map that assigns the expectation value to an observable of the system. That's the essence of what a state is. Okay, so observables are operators on this finite dimensional Hilbert space, matrices, linear maps, and the quantum state is the map that in a linear fashion assigns an expectation value to each of these observables. And as I said, this notation rho psi comes from the fact that even if I have a pure state defined by a vector, I may want to emphasize I have a density matrix for it, which is a rank 1 projection. And here I sort of made this abstract definition we will not use very much, but it's sometimes good to keep in mind. I will only indirectly refer to it. You can do this a little bit more generally. For a system that has a C-star algebra of observables or a star algebra of observables, it's some linear operators on some Hilbert space. There's a star operation, you can take the adjoint. And whether or not it's finite dimensional, it doesn't matter. You can define states, and they have to satisfy the fact that they make a linear assignment of expectation values to observables. And it has to be positive. You put in a positive observable, a projection, for instance, it has to give you a non-negative number. And it has to be normalized. Put in the identity, you get 1. And in fact, if you apply this to finite systems, you exactly get the functionals defined by density matrices. So this is not sort of a new notion. It's exactly what you already know. Okay, so, but on this slide, probably there isn't anything new either. You know, if you're interested in QIC, then what's so important about states in quantum mechanics, quantum systems, is that they can be entangled. That's something we don't have in classical systems, and it's what makes quantum information tick. So, it's usually defined, at least mathematicians would always define it like that. You don't really define what is entangled, you define what's separable, which is the opposite. And And so let's just focus our attention on bipartite entanglement. That means we have divided the system into two subsets, two disjoint subsets. So A could be the first 5 qubits and B could be the rest of the qubits. Then with respect to that decomposition, a separable state is one that can be written as a mixture of vector states that have the structure of a simple tensor product. Okay, so if they're mixed state, they're mixed, but you can write it with vector states that are simple tensor products like so, where this is a state of the system A and this is a state of the system B. Anything that can be written like that is entanglement. And in particular for pure states, it just means that if you can't write it as a simple tensor product, there is a certain amount of entanglement. And I'm sure you also know that it's easy to detect. You may have a vector given in a certain way, and maybe it's not immediately obvious that it's a tensor product or that whether it's not. But you can spot them by looking at either the Schmidt decomposition of the vector, or more directly, you can just say, you can look at the entanglement entropy. Sure, you have seen this definition before. It's defined as follows. So with respect to this decomposition in A and B, I define the density matrix rho A, that is the partial trace of my rank 1 projection that defines the pure state C, over the Hilbert space of the part B of the system. That gives me a density matrix. And the entropy of that density matrix is the entropy of entanglement. Entropy defined, as Van Neumann did, as minus trace rho log rho, which as a formula is just the same as the entropy of the probability vector you find by putting the eigenvalues of rho in there. So you can diagonalize rho and calculate it like that if you want. Negative sum over I, rho I log rho I, when rho I is an eigenvalue of rho. So that's the phenomenon entropy. If it vanishes, the pure state was separable, and if it's positive, it's always not negative, and if it's positive, it's entangled. Okay. Well, don't be offended if I give you an example. This example is the simplest one, but it's often good to give simple examples. So you have the Bell state. I didn't even write what A and B is. It's a state for Q, 2 qubits. So A is the first one, B is the second one. They are here in this, it's a maximally entangled state, as it turns out. You can write the density matrix that is associated with this vector, C Bell, this should have been, the rank 1 projection. And then the prescription for the entanglement entropy is to compute the partial trace, say with the second system, which is, we consider this as a 2x2 matrix of 2x2 blocks, and we take the trace in each of the blocks, and we get 1/2 and 0 and 0 and 1/2. This density matrix, and it's diagonal. The eigenvalues are 1/2. I have 2 of them. So this formula gives me log 2, which is the maximal possible value for a two-dimensional component of a bipartite system. And here is an interesting fact. So this is true in general. So if the part A has a Hilbert space of dimension dA, then the maximal possible value for the entanglement entropy that you can get is log dA. Actually, it's the minimum of log dA and log dB, where dB would be the dimension of B. So then there is this result, which, when there's much more information available about this, but the interesting thing I want to point out is that if you choose a pure state at random, maybe it's found by applying a random unitary to a given state, or maybe there's some other way, then almost always you will find that the entanglement entropy is near its maximal value if the dimension of the system is large. And you can actually quantify that, and we don't need to do that. I just want to make the point that if you ask what's the probability that my entanglement entropy is, say, 99% of the maximal value, that probability will tend to 1 as the dimensions grow to infinity. So this has been proved in various ways, and it's not very complicated. And in fact, a whole lot of more detailed information is available. And I point here to what happened here. Did I call? Oh, no, let's move to the side. In this paper by Patrick Hayden and Leung and Andreas Winter, there's a lot more information about entanglement-like quantities and entropies and how they behave for random vectors in large dimensional systems. So for us, it's at this moment an interesting fact. Okay. So not sure why this seemed to disconnect, but I have to.
Put the screen once and then.
Okay. All right. So entanglement usually maximal. I'll connect this to this question here, which I want to spend some time on thinking about. How to specify a state? Well, it's very simple. You can decompose it in a basis, and you give all the coefficients, and that's the information that determines the state. How many coefficients are there? Well, as many as the dimension of the Hilbert space, which if it's a product of n qubits of dimensions v1 up to the n is the product of dimensions. So it's all qubits, two-dimensional ones. It will be 2 to the n. You don't have to worry about an overall phase, but essentially it's exactly this exponentially large number. So, and if the state is chosen at random, there's no way to compress this information. There's this full complexity. And I don't need to tell you, this number very quickly becomes intractable in almost every way. Maybe not for every mathematician, but from the moment you start to do something practical or compute on a computer, it's impossible. But as we as it turned out, as we have learned, the states that we encounter, the states that we are interested in, maybe states that are realized as ground states of Hamiltonians, or short-range interactions, or states that can be prepared by a quantum circuit that isn't too enormous. Some low-depth circuit of unitary gates. They turn out to be atypical in this respect. They are not all that entangled, and you don't need that many numbers to accurately describe. And so I want to explain this a little bit, where this comes from. And the gateway to this is often taken to be area loss of bipartite entanglement. So the first thing we're going to look at is the entanglement of such a state that we come across in the lab or as a result of simulating a ground state of a Hamiltonian. And you look at its entanglement and find out that there's something interesting about it. It's not maximal. And just to fix the ideas, let's sort of look at a qubit chain, and it's just nearest neighbor interactions. So I have a self-adjoint matrix acting on 2 of the qubits. For simplicity, you can assume they're all the same dimension. This can all be generalized. That's not the point. Then if you add up the interactions, you get a Hamiltonian, you get a big Hermitian matrix of the dimension of the Hilbert space. And since it's Hermitian, of course, it has real eigenvalues. I can order them. So here they are, lambda 0 n less than lambda 0. They may be degenerate, but I just list the distinct numbers that appear as eigenvalues. It's a big list. Typically, there may be some degeneracies, but the dimension is exponentially large. It's d to the n. Number of eigenvalues is also going to be exponentially large. The size of this matrix is order n. If these are uniformly bounded, say, all norm 1, so then the norm is less than n. And so these eigenvalues will all appear in an interval of length n, say between -n and +n. That is exponentially many. Usually they will be piled up very densely, almost everywhere. But it does happen in many interesting cases that if you look at the ground state, which is given by an eigenvector belonging to the smallest eigenvalue, that you see a gap. And it means the following. We say that a family of Hamiltonians is called gap if there is some positive number, so that the distance between the ground state and the first excited state, between these two eigenvalues, is bounded below by the positive number gamma for all n. Now, I'm not going to talk very much about physics. I mean, we have so in mind that we would do this for families of Hamiltonians that are not chosen at random either, but they maybe describe magnetic system of different sizes, and it has the same characteristics as I increase the size. So it's some systematic family of Hamiltonians. Okay, so for this kind of system, under this assumption that it's gapped, so if this family Hn is gapped and has a unique ground state, say Cn, then and we consider a one-dimensional system, so I'm going to make a bipartition by selecting an interval from A to B, maybe the first n over 2 spins, and then my B part is the next n over 2 spins, but it could be some other interval that I choose. Then actually the entanglement entropy is uniformly bounded by some constant that doesn't depend on the size of the system or the choice of A and B. So this is called an area law. So this is area law in one dimension that Matthew Hastings proved. The first area law that was proved. And it's called area law because that constant here you can think of as the size of the surface area of an interval embedded in a bigger one. Indeed, it's just 2 points. It's constant. So that it's proportional to a constant and not something that grows with the volume is what is called an area law, and you can generalize to higher dimensions. If you have a two-dimensional system, you cut out a big square, then you expect for a gapped system, and some examples is verified that the entanglement entropy for such a system is only proportional to the perimeter of your square, not the volume, not the area of your square. So area refers to one dimension less than what you have. Okay, so that's Hastings' area law. Well, there's some other, it's turned out to be a really interesting thing to think about, and we will look at some consequences in a second. But because it's important, people also thought about maybe area laws can be obtained in other ways. So let me focus on another result here that looks at states that are exponentially clustering, have only short-range correlations. And for simplicity, again, let's take a spin chain, and maybe just one consisting of qubits doesn't really matter, but we have to look at general correlations. So that's why I'm introducing here these sets X and Y in which I can have observables. So the operators I'm going to look at localized in a subset X, a finite region X of the integers chain. I will put them together in a subalgebra of observables that I have, A sub X. And then I can do the same for Y. And I'm going to be interested in a situation where X and Y, these two sets, are separated by some distance. The distance is defined in the usual way. So these are sets. Now, the distance between the sets is just the smallest distance between a point in one set and a point in another set. Since you're doing everything in one dimension, I didn't draw too many pictures because I think you know how one dimension looks and how to measure distance. Okay, so then the kind of exponential clustering we're looking at is as follows. This is exactly what in the paper I'm going to cite is needed. That's why I'm defining it this way. It's sort of like it's parameterized by two numbers, a correlation length C and then some basic length L. We say that a state of n qubits has CL exponential clustering if for any observables you choose on this subset X, an A on subset X and a B on subset Y, that are at some distance greater than L, the correlation is bounded by this exponential bound. So this is the expectation of the product of the observables, AB. This is the product of the expectations. So the difference is the correlation. And so the absolute value of the correlation is less than norm A, norm B times its exponential. E to the minus the distance between X and Y over this correlation length C. And then Brandau and Norodetsky proved that you have an area law for such a state. There's no reference here to a Hamiltonian or a spectral gap. It's purely based on the fact that you have this quite uniform bound on the decay of correlations in the system. And they can give a very simple upper bound, in fact, for a constant. So, so this is a result similar to this. And in fact, in the paper of Hastings, he also gives an estimate for this constant. And it's not very nice. It's some complicated formula. But this is kind of an improvement. So the entanglement of any finite region is bounded by this constant. It's some universal constant times this length L here, times the exponential C log C, where C is the correlation length. So it's a fixed number. This is not a growing exponential or anything. Okay, that's another area law. All such states with good exponential decay of correlations also satisfy an area law. It's also in one dimension. I'm not going to talk about area laws in higher dimensions today. I mean, there are results and people are improving on it regularly. It's a very interesting subject. It's not fully solved, but there's interesting progress to talk about, but there would be another lecture. Okay. So I like, if I can, to connect concepts. So we talk about area law, we talk about spectral gap, we talk about exponential clustering. So here is a connection between spectral gap and exponential clustering. And let me again do it in some simple context, but in fact, you can do this not just in one dimension. This you can do in any dimension. So I said here the lattice Z nu, you can take more general things, but suppose you have some Hamiltonian on a system of new dimensional cubic lattice. And I'm going to generalize. We had nearest neighbor interactions before. We can take some finite range interactions. Maybe it's nearest neighbors in all directions, or maybe it's also next nearest neighbor, up to some distance r, right? So here this notation is the ball centered at x and the lattice of radius r, and so all these terms that I have in the Hamiltonian are contained somewhere in a ball of radius r. And I'm also going to assume that they are uniformly bounded. So then we know for quite some time now that if you have a family of Hamiltonians like this, with a gapped unique ground state, then these ground states have exponential decay of correlation. They're exponentially clustering. And in the case of one dimension, which is for which Brandao and Radetzky formulated that condition, it's exactly this type of clustering that is uniform, the Xi-L clustering with some choice of the constants Xi and L, which you can estimate in terms of the data here, the dimension and this M and so on. The exact numbers are not that important, but that you can do it in general is what's important. So then let's summarize where we are now. So with this, spectral gap implies exponential clustering. And we know that exponential clustering implies area law, at least in one dimension. So these things are connected. And area law is way less entanglement than the typical entanglement you would find in a random state. So we haven't actually looked at any state so far. So maybe we should look at some state. Let's go back. And try to connect area law to low complexity states. I mean, it's relative to say exactly what low complexity means. It'll be pretty complex, but not as complex as a random state. And here is a class of examples, which is very useful to think about, so-called matrix product states. And they are indeed an example of a large class of low complexity states that we introduced a long time ago. And let me describe it to you in some slightly simplified context, but good enough for what we're talking about here. So let's take n qubits. So let's take them all of the same dimension for simplicity, otherwise we need to introduce too much notation. And well, we already saw that in general, of course, the general state, can decompose it in a tensor product basis, computational basis, and I have lots of coefficients. And there's no way to compress the information needed to list these coefficients in general. For a random state, it's maximal complexity. But for a matrix product state, you do the following. So you define all these coefficients in terms of a small amount of data. Namely, you take D, where D is the dimension of the qubits, capital D times capital D matrices, where capital D is a number you choose. It's often referred to as the bond dimension. It has other names. And so I have, so MDC denotes the D by D matrices with complex entries, and I choose as many matrices in there as the dimension of just a single qubit in my system. Then I've also picked 2D dimensional vectors, and I define coefficients C for the state that I will construct by this kind of formula. It's the alpha beta matrix element, but alpha and beta are the vectors I've chosen, of the product of the matrices that correspond to the indices of the coefficient I want to define. So this is AI1 up to AIN. It's just n matrices that I multiply, or this should be a capital N, sorry. And that this is the coefficient in the matrix product state. So the data are far from exponential, right? It's D by D matrices, that's little d by capital D squared numbers, and then two vectors, that's 2D. So that is, if you want, comparatively a very low complexity state. The information that I put in can be summarized in just this polynomial number of, bounded number of complex coefficients, I should say. It doesn't even depend on the size of the system. Okay. And it's kind of interesting sometimes to think about this. So you plug this in here, you get a vector, but I can think of it as a map of the choice of vectors I'd make to vectors in the Hilbert space of my system. Right? So it's just a map, and you can think of it as a rank 1 projection if you want, or it's just two vectors. It's a linear map that gives you, with this formula, a vector in the Hilbert space. And it's often useful to write this in diagrammatic form. I don't know who first did it. It wasn't me, but it's very useful. I know that, you know, the whole school around Ignacio Sirac and Verstraete and Perez Garcia and so got a lot of mileage at showing in these diagrams what the structure is of these coefficients. So you think of a vector, a state as a vector in the Hilbert space. It's a thing with indices, and you should be able to find the coefficients as a function of the indices. And here are the indices, I1 up to IN. And the idea is that in this diagram, what this A is the set of matrices, often called a tensor because it has an additional index. Right? It's an index set of matrices. So it has the matrix indices, but then it has this additional index. And then the green lines here in between mean contraction of indices, which for matrices means multiplication of matrices. So this says I have to take these matrices according to the indices and then multiply them. And then I contract with the vector beginning and end. So that's just the product of a matrix and a vector. So this picture represents the state. And one thing it's useful for is the following. So I want to show you, it's very simple to see that these states satisfy an area law. And so now at this moment, I don't have information about a gap or exponential decay or anything, but we can just see the satisfying area law. Well, I try to do here what one should do. You take the density matrix or exponent to C, and then you do the partial trace outside some interval AB. It will give you a density matrix on the interval AB. And I kind of wrote this with the idea that you would conclude you didn't want to see it. Because if we use a diagram, we can immediately get to the information that we want, and at least in this case. I'm not saying formulas are not important. The diagrams are good too. So what I'm going to show is that the rank of this density matrix is at most d squared, and that means that the entropy of it is at most 2 log d, the log of this dimension. And let's see how that goes. This is not very beautiful artwork, but I hope it does the job. Okay, so I have to construct this rank 1 projection on C. So I have 2 copies of C. So they're here. And well, each have their indices, IA to IB, and then the other one JA, which should be an A to JB. And then I'm going to take the partial trace, which is I'm going to contract all these indices that corresponding positions, right? So this is the chain and contract all these. And well, the question is, what kind of object is that? If I look at it as a map from, say, the bottom to the top, or if you want the other way around, if you think of these as the indices in some domain Hilbert space, and I map it into the vector in the target Hilbert space, what kind of map is this? And what I see is, if I do that, I didn't want to really put this picture in here. I mean, one could. But the important thing to observe is, so in here is everything that happens in this picture, except that I have these indices that are not considered as input and these as output. And what I see is that what goes into the output all has to go through these red lines. That's the only way to get to the indices in the output IA to ID. And what are these lines? There's contraction over the d-dimensional space. So that means that you can think of this map as a composition of maps, but somewhere in between you end up in the tensor product of two d-dimensional spaces, CD, tensor CD. And then you map on further, you create something bigger dimensional. But if you have a linear map that is a composition of linear maps, and somewhere it goes through a space of small dimension, say d squared in this case, the result can never be more, the range can never be more than d squared dimension, right? So that's why we immediately have this bound here on the entanglement entropy of any part of the chain that you select. It's at most 2 log d, and so it clearly satisfies an area law. Okay. Now, maybe it's nevertheless related to these other properties that I talked about earlier, but I haven't discussed in the context of these states. So let's have a look at that. Exponential clustering. So we have to look at long-range correlations. And now I'm going to do this in the matrix product state. And I want to show that these long-range correlations are entirely controlled by a finite dimensional object called the transfer operator. So the kind of thing I'm looking at is as follows. So in principle, I have to take a general observable x and y on some finite set of the system. For simplicity, let's take two operators that act only on one qubit. So x acts on qubit number 0 and y acts on qubit number n+1. So that in between, I have n qubits on which I don't have an observable acting. So I just have the identity acting there. And now I can again write the diagram for the expectation value of this thing. And so it will look like this. So I'm not contracting all the indices without modification. I do this for most of the qubits. You know, if x and y were also identity, I would just compute the norm. I would contract everything. I have the norm squared of the vector. But since I have an x here, it's not just Kronecker delta. And I have a y here, it's not just Kronecker delta. And I have my tensors here, these dots now, they represent my tensors A. And I have to, if the index is I have the I matrix of this tensor with 3 indices, I have J, I have AJ. And so if I start contracting from the left, then you can imagine with a little bit of goodwill that I'm coming from infinity, I'm contracting, and then I come here, I'm not just contracting, I have to take all values of I and j and multiply by the matrix element of the observable that I have, which is yij. And that's why what I'm going to get is a matrix that is of this form. I call it EY1 here for a reason that will become clear in a sec. And then I'm going to continue contracting again with the Kronecker delta because there's no observables there. And that will give me the map that is this red contraction here. It gives me this red map that is going to transform this matrix in a new one by applying the same formula, but now with I and j equal to each other. And so summarizing this calculation, to really see what's happening, you probably should do this at home. It's homework. Do we do homework in this class? So, well, I've cheated a little bit. For this to work well, especially this contracting from plus infinity, this is going to run into trouble, almost certainly, as you know. You have to normalize things carefully if you want to get something that is non-zero and non-infinite. So I'm going to do that. And in fact, there's some other canonical choices that would be well advised to make. The matrices that define the matrix product state, they're not uniquely determined by the state. There's some freedom there, some gauge freedom. And you don't have to go into it, but it is a theorem. It's a fact that you can choose them so that this transfer matrix E that I defined becomes your beloved object, a quantum channel. It's a completely positive map. I consider it as a map on the matrices of the dimension D, which is the bond dimension, and it's of this form. It's written in Krauss form, right the way it comes. And if you normalize things correctly, then it actually is also unit preserving, and E of 1 is equal to 1, which means that 1 is an eigenvector of this map with eigenvalue 1. And then it's also immediately the theory of quantum channels that the norms, and that's actually the largest eigenvalue. This is also the norm of this map. Maps like this, the norm is equal to the norm of the value in 1. Okay, so now I go back at calculating correlations, and I usually get another notation for my correlation. So I have an observable at 0, I have an observable at n plus 1, and I have all these ones in between. And if you go back at the sketch, the picture, what I was really saying is that this is a linear expression in which appears the nth power of this matrix, or this linear map E. And it's a map of finite dimension, fixed dimension. And I'm taking a high power of it. And that's going, the behavior of that is going to tell me what the behavior is of the correlation functions. And you can figure out exactly what you have to put here. You have to take in a matrix element of this large power of n to get the correlation function. And so the eigenvalues of this E will determine what the long distance behavior is. And in particular, if 1 is a simple eigenvalue and there is no other eigenvalues of magnitude 1, then the n power of E will essentially be a rank 1 projection. It's not a symmetric matrix in general. So the row here, in fact, is going to be a left eigenvector of E, which doesn't have to be equal to the right eigenvector with eigenvalue 1 that I have here. And so you get a rank 1 projection on the projection in the matrix space given by these the two eigenvectors 1 and rho, plus a correction that is of the order the nth power of the next highest eigenvalue, which will be an absolute value, strictly less than 1 in this case. And so if you plug this in, you will see that this exactly factorizes. This becomes the product of the two expectations. And the difference is of order is lambda 1 to the power n. And that's why these states in general have exponential decay of correlations. Now, there's some other things that can happen when the eigenvalues, the eigenvalue 1 is not simple. Then it means your state is going to be mixed, and it may be a composition of different ones. Or there may be other eigenvalues of absolute value 1. That means there's some periodic structure in your system, but that's not the case. But even then, you can just decompose, and in each of these components, you will have exponential decay of correlations. Okay. So matrix product states have exponential decay of correlations. You're not surprised, they satisfy an area law, which we already could see from the beginning exactly what it was. What about spectral gaps? Well, it's indeed true that these are ground states of finite range Hamiltonians with finite range interactions with a spectral gap. So it's also a general theorem. You can take one, or you can take a finite set of translation invariant or even periodic pure matrix product states that have this exponential decay of correlations, for which the map E, the transfer operator, has just a simple eigenvalue 1. And then you can you find a finite range interaction so that this Hamiltonian here will be a family of gapped Hamiltonians with exactly those states as the ground states. Whether it's unique or there's any finite number, this can be arranged. So also this way we see that, yeah, there's an area law because these are ground states of gapped Hamiltonians. Hastings group, then yeah, let's carry on. So we have all these properties for the matrix product states that went together, and I think for every scientist, not just a mathematician, it's kind of interesting to ask, is there some converse of this? And well, it's not quite a converse, but something almost as good as a converse, which says the following: that if you have the ground state of a gap finite range Hamiltonian for a one-dimensional system, then it can be well approximated by an MPS. So these states that have a gap and exponential decay of correlations and an area law, and are the ground states of gap Hamiltonians. These are, by the way, ones that we could very stably produce and see as a result of natural physical dynamics. You will be able to approximate it well by an MPS. So what that means exactly technically, I decided I'm not going to put on the slide. Basically, it means it's not the case it will be matrix product state with some bond dimension capital D. But if you take capital D large enough, you will be able to get as close as you want for any expectation value that you would calculate. There is some very precise word that tells you how close can you get, or if it's non-homogeneous, what you have to do when you have long systems. You want to look at long-range correlations and things like that. So there's many papers on this. I could give two very good ones, but I think are very good ones. One by Arad, Lando, Vaziran, and Vidic from about 5 years ago, and then a little bit later, Donzel and Randall published another paper. Yes, Isaac?
Just approximating certain expectation values.
Right, so there's actually different results in these papers. So that is the focus, in particular, this paper of Donzel and Randall. Their arguments are optimized to approximate certain, all observables in a certain region as well as you can. You can also ask, if I take the norm difference of these vectors, when is that going to be small? But that's, in many cases, asking too much. But that is discussed in these papers. And by the way, this is, with hindsight, also the reason behind the incredible efficiency of the density matrix generalization group as a numerical method to finding such states for Hamiltonians you may be interested in, if you're a physicist. So this numerical method was invented by Stephen White, but at the same time that people came up with matrix product states. It took a little while to understand exactly what the connection is. But it turns out it can be interpreted as a variational method in terms of matrix product states, in the sense that it can be made arbitrarily accurate if you increase, it is as if you're looking for the best matrix product state of a given bond dimension. And if you allow that bond dimension to grow, you can improve your approximation.
Is there any specific reason why that finite range
so I don't know what the reason is, but I could say the area law is a reason. They have low entanglement. That's why I can do it. But in mathematics, there's nothing is really a reason. There's just one thing implies the other. But that is what, if you didn't have that, if you did have some arbitrarily large entanglement, or even just significantly larger entanglement, then that efficient approximation would have to go down the drain. Well, you know that because if you have bond dimension D, your entanglement is bounded by some simple formula in terms of the bond dimension. So that's sort of the closest I would say you can give a reason.
So is there anything specific about MPS states apart from low entanglement?
Well, there is this explicit formula that allows you to calculate expectation values, or energies, correlation functions. I can tell you other things. I mean, it is connected to it's sort of a quantum version of models that people construct in probability theory to model data that are just a little bit more complicated than simple Markov chain, for instance. But maybe you can discuss sort of offline some other time. Okay. So it's sort of hard not to mention this example. And maybe everybody knows it, but I think oh, I lost my clock. It's the most famous example. It's the example that started everything. By everything, I mean matrix product states, area law, and it's the EKLT chain. So it's a specific spin-1 chain with the nearest neighbor interaction that Affleck, Kennedy, Lieb, and Tasaki introduced and studied. And it has the following interaction. So for the physicists among you, this is sort of obvious what they mean. This is the vector of spin matrices. It's an isotropic interaction. It's not just Heisenberg. It also has this other term, Heisenberg squared. And in fact, this combination is equal to the projection, the orthogonal projection on the spin-2 states for a pair of spin-1s. So this is a spin-1 chain. It's Q-trix. It's a three-dimensional Hilbert space for every spin. And they introduced this model to show that indeed what Haldane predicted as a big surprise, in fact, in 1983, namely that there are antiferromagnetic type spin chains for which the ground state is unique, is disordered, has exponential decay of correlations, and has a spectral gap above it. You can argue, I mean, how big the surprise should have been, but before this, most models that were sort of non-trivial and you could solve exactly, they were solved by beta ansatz, and they're critical, and there's no mass gap, and there's power law decay of correlations instead of exponential. But Haldane says, no, there's a whole other phase out there, and it's not just a one point, it's a stable phase, and you should have it without this term, but Affleck, Kennedy, Lieb, and Tasaki couldn't prove it without this term, so they added this term and found all these beautiful properties. In fact, it's still not proved without this for this Heisenberg model by itself, to a mathematical standard. What I took this picture from the paper of Affleck, Kennedy, Lieb, and Tasaki just to show you they almost wrote a diagram for the matrix product state, but it was a little different. They called it valence von solid construction, where the tensors were sort of constructed in pieces. They were decomposed. These two dots are qubits, spin-1 halves. This circle denotes symmetrization, which is multiplication by a projection. And then these are also contraction, but they did contraction in the singlet state because they had this SU2 invariant model. It's sort of interesting to look at the SU2 invariance of the resulting state. But it's equivalent. It's a simple gauge transformation to use the contraction with either a Bell state or a Kronecker delta, if you want. And there is some interesting, so let's see, I should move along. There's some interesting structure in this state, which is called string order, which I wanted to mention because if we go to our two-dimensional example, we will sort of see something similar. And this is sort of the first indication that in fact, this is a disordered state, but it has some interesting structure if you take into account the symmetry. And sort of the first example of a non-trivial symmetry protected phase, which is a big topic nowadays, but maybe a little bit to the side of the main line of my talk, so I won't say very much about it. And you see it if you decompose this in a basis, it also has to do with its low complexity. So if you decompose this state in a basis, the computational basis, say the states of S3 equal 1, 0, and -1, then you find that the only non-zero coefficients come for states where the 1s and the -1 strictly alternate in the sequence. So it's much less disordered than it could be. So the zeros are sort of swimming everywhere, but then there is a -1, 1, -1, 1, -1, 1, and so on, which is also as a consequence of the fact that this is a state of total spin no more than 1. But it also shows you directly the low complexity of the state. Okay, so maybe quickly, the toric code model. We want to not stick to one-dimensional systems forever, especially not if you're interested in applications in quantum physics. So much interesting physics happens in 2 dimensions. So here's the toric code model. I will just briefly introduce it. It has short-range interactions. They are not just nearest neighbor. They come in these 4-body interactions. So what we have is qubits that are sort of conveniently described as sitting on the edges of a square lattice, these dots. And the interactions are written here. So the 4 qubits that surround a vertex of the lattice are given an operator AV, sometimes called star operator. It's a product of the first Pauli matrix associated with these 4. And for a face of the lattice, a plaquette like this, the 4 that sit on the edges around the face are given third Pauli matrix. You take the product of that. These are operators with eigenvalues plus and minus 1. If you write it like this, you write a Hamiltonian that is a sum of positive terms, and it turns out you can construct an eigenstate that is eigenvalue 0 for each of these terms, and therefore also for the Hamiltonian. And it turns out to have a whole host of interesting properties. You should have another talk on this, maybe sometime. But the only thing I wanted to say is that this is an example of a model for which you construct the exact ground state, not as an NPS, but the 2-dimensional generalization of an NPS, usually called tensor state, sometimes PEPS. And I'm not going to say very much about it. And I could discuss all the same things. And what about correlations? What about area law? And there's many things we know, and there's just as many things we don't know. But this is a very good up-to-date review paper here by Ignacio Sirac, David Perez Garcia, Norbert Schuch, and Frank Verstraeten that I can recommend to you. So but the point is that now, instead of these matrices that you pick from a set indexed by the states of your qubit, it's not just, they're labeled now also by the sites in maybe the square lattice. So this is the physical index sitting here. And instead of matrices that have 2 indices that you can contract with your left neighbor and your right neighbor if you make a product, now you have a tensor that has an additional 4 indices because in the square lattice you have 4 neighbors. And the state is constructed, coefficients, if you want, of an expansion in the computational basis is constructed by contracting these indices between pairs of neighbors everywhere. This is computationally by itself kind of an interesting problem how to do that. But again, you have a low complexity representation of this class of states. Okay. Well, these proving spectral gaps are so important. And hopefully you have some methods, and for a while I thought they had some good methods. I'm not going to explain them in detail. This is an interesting subject. There's a finite size criterion by Knabe and some other methods that people have used to prove spectral gaps for interesting models. And so, you know, after you do a few models, you start feeling good about yourself. But situation is not that great. So even for these simple Hamiltonians of which I gave examples in general, the question of whether the spectral gap is open or not is undecidable. This was a paper entitled Undecidability of the Spectral Gap by Cubic and Perez Garcia and Wolf. It appeared in 2015 in Nature. They could publish it quickly because the Nature editors, they don't ask whether the math is correct. But 7 years later, it was eventually published. It's a very long, complicated paper. It's 130 pages or something. I think the math is correct. I was the editor for this one, so I think it's correct. But here it's sort of interesting. So here's the end of the abstract. It says our result implies that there exists no algorithm to determine whether an arbitrary model is gapped or gapless, and that there exist models for which the presence or absence of a spectral gap is independent of the actions of mathematics. That sounds like pretty scary. So, but this is very interesting, but you should not worry. Because there's still good news. We can continue and try to improve what we know about proving spectral gaps, and people do, and they succeed. So very quickly, 2 examples, and then I'll stop. Okay. So for the EKLT model, the analog in 2 dimensions again, for which a tensor network state is the exact answer, etc., etc. But it's a model with 4-dimensional spins at each side on the honeycomb lattice, and it has a similar interaction. It's just that now it's the projection on total spin 3 for each pair in the honeycomb lattice. With the aid of some computational assistance, almost simultaneously 2 proofs were given. They are related, but they're not the same. One by Pomada and Wei, and another by Len, Zandik, and Ben, just 2 years ago. So that's great. I mean, there's a long history about this model, but I have no time to sort of discuss it. I mean, it was conjectured that there was a gap. It was introduced originally in 1988 by Kennedy, Lee, and Tasaki, and after Kennedy, Lee, and Tasaki. So it took a long time to actually prove it. So finally, I can't resist. Here, another really interesting model for which we also can prove there's a gap, and for which it's relevant. It's a model for the fractional quantum Hall effect, and we'll give just one version of it. It's for the new equal 1/3, the 1/3 fill, lowest lambda level, fractional quantum Hall effect, in a cylinder geometry, which means that instead of a 2-dimensional plane where we have electrons subject to a perpendicular magnetic field, we have periodic boundary conditions in one direction, and so my plane is rolled up to be a cylinder. You can, without interactions, there's also a model you can solve exactly. You can find the orbitals that span the lowest lambda level. What Duncan Haldane did in 1983, he proposed a Hamiltonian that incorporated interactions between the electrons that sort of totally changed the spectrum. So instead of the degenerate orbitals in the lowest lambda level, you get some interesting spectrum with a gap exactly at 1/3 filling. And so he conjectured that there was a gap. It also took a long time to prove it. I have the details of the model here, but maybe in the interest of time, I will not give it to you. It ends up being equivalent to a finite range Hamiltonian of spinless fermions. And in the last couple of years, we obtained the proof of the spectral gap, and the most complete result is due to Amanda Young and Simona Wartzel, published just last year. The expression is not terribly important, except that it suggests that it's not a very simple proof. There's different cases, give different estimates, and so the gap of this Hamiltonian is bounded below by a positive constant. You can give explicit values of it, but it's mathematics we don't need to go into. So I'm not scared of the undecidability of the spectral gap in general. There are interesting models, and if they are interesting, it seems like you may still be able to prove it for the special cases. Okay, so I'm not going to say much about these other topics. We will leave them for another moment because it's 4 o'clock and I want to stop on time. Thank you.
This may be a naive theorist point of view, but I'm imagining these models have something to do with things that might exist in the laboratory. Yes. And you can measure correlations and so on. So what does undecidability mean from that point of view?
Oh. Well, so in the paper, they showed you how in principle you can construct a model that will, so these all these families of Hamiltonian, but large distance, where you construct it at a certain scale, and then larger box, and larger box, and larger. And what they show is that you can construct models that seem to keep changing their mind for forever. But you don't know whether they will keep changing their mind or not. So it's so logically, or in the language of computer science, there's no solution to the halting problem for that question. If they have data in a certain number of moments. They are not as far as I know, Hamiltonian is about. Even in an artificial system, cold average system or something like that, I don't think we will use it. But even if you could, I bet you're going to find it.
It sounds like it could, because I could build one system that behaves one way and then increase it, and maybe it behaves another way. So
That's right.
that kind of.
That's right. And you don't know whether finally you have found what the asymptotic behavior is. And so the group you can't know, but asymptotic behavior behavior. That's more or less how it works.
So it could be a signature that systems are erratic in their properties that you change.
It certainly, given that result, wouldn't be a surprise if you would find in the lab systems that seem to behave erratically in that sense. And they're precision models that finite things interactions, simple things, they're not very complicated. But they've carefully chosen coefficients. So that would be a challenge, I'm sure, in the lab to tune them exactly the way they want. It's mathematics. But if you thought you could come up with an algorithm and you plug in any Hamiltonian to get out gap or no gap, well, that's not going to work. But many computational physicists probably didn't expect this either.
So a related question from a mathematical standpoint, how does it relate to the sort of compactness of the packaging of how many bits of data have to specify the bits?
You mean the undecidability?
The undecidability for the gap. It's like you have alternation between some polynomial number of to be specified conditions.
Yes.
How much many more?
I know how to construct the Hamiltonian, but I didn't know what the state is in some sense surprisingly simple that you have to give this as input they use the tiling block that is also not decidable. And it's of course an aperiodic tiling of Penrose, but in the case of Penrose, we know we can tile it. You can design problems with finite number of pieces, and nobody will ever know whether you can tile the whole thing. And so now what is the complexity exactly of that? It looks simple because it's only finite number of pieces. Simple rules. From that point of view, it looks that the input is not very complex.
So I had a question actually. So this proof of that for like 2D HLT models, like this computer assisted.
Yes.
Like for me, like that counts as proof, but I was wondering because like these are like big computations, right? Like, so I was wondering if this, I mean, like, if mathematicians actually view this as a legitimate proof or not.
Right, very good question. So I called it computationally assisted. I did call it proof. So maybe I took a position. But it's not a computer assisted proof, which has a very specific meaning. Right? You can have very complex proofs and you have to check 11,000 cases, and there's no way you could do it in your lifetime, but a computer can. Okay. If there's a way to check the code and everything, and everybody agrees, then there's no reason to doubt that the computer did it, and you have a proof. This is not of this type. You need to do diagonalization spectral. You need to answer spectral questions for very large matrices. And they are not fully exactly diagonalizable with the computers that we have to do. And so then, but they're also not the same for the two. So I think one is more, I would say it's closer to real proof. You do Langshows for a very large matrix, but maybe it's good. The other one is more complicated. And so I also know that some people get upset that people publish theorem, proof, and then you read and say, well, this is not really proof. I don't necessarily get upset. But it's also okay that some people are still looking to actually find a mathematical argument or just close the, I mean, it could still be computer assisted, there's ways to do it that is actually acceptable in the mathematics literature. It hasn't been done yet, and people are trying. So I think it's because I mean, some things we can compute very well. So, for instance, Haldane's conjecture that the spin 1 antiferromagnetic chain is gap. That's not a very complicated system. There's very good computations. There's very accurate calculations of the energy and the first excited state. The gap is, in a sense, known to 8 digits or something. So I don't know too many people who are trying to find a proof of that. But still, it could be interesting because, so why is it we can't prove it for that model and we can prove it for other models? I think it's nevertheless an interesting question.
Yeah, so thanks for a really good intro to this topic for experimentalists as well. I wanted to connect a little bit of these models. What were you motivated by in terms of experimental realization? So, for example, the example you gave with the qubits, what were the interactions within the chain? The nearest neighbors or is this like, is your theory agnostic to this and the field doesn't necessarily focus on just one?
No, so the one with the qubits, the DKLT chain. So people really wanted to know about the Heisenberg interferomagnetic chain, for which there are real systems that model it. With some magnetic polymers that you can model quite well by that model. But they did instead modify the interaction so that it became projection on spin 2 states. So it means they give energy 1 to when the spins are parallel in the ferromagnetic state. It is a model that has the isotropy, SU2, and favors short-range antiferromagnetic correlations. And that's what Haldane was talking about. There's such a phase where you find a disordered state. You have short-range correlations of antiferromagnetic nature, but there's disorder overall. And moreover, there would be a sort of a topological property somewhere hidden in the state. So there's certainly enough motivation. Moreover, Haldane actually didn't specifically say, if I remember correctly, certainly not in the original papers, which Hamiltonians would have this problem. He was just saying there isn't just the critical phases, there is also this phase, this massive phase. And it should be stable, and it's some region in the phase diagram where you will find this. So from that point of view, I think Affleck, Kennedy, Banasaki were well justified saying, well, maybe we modify the Hamiltonian a little bit, maybe we'll be able to find the representative at least of this state. And so the phase has been found experimentally. Maybe the Hamiltonian is not exactly this one, but we have also now mathematical understanding that such phases are indeed stable. You can modify the Hamiltonian as long as it's not too much, and the qualitative properties will remain the same. So
I have a slightly CS theoretic question. Some NP-complete problems like MaxFit and so on can be reformulated as ground state of local Hamiltonian form.
right.
So, by any chance, do you know, like how hard or easy it is to write down a Hamiltonian corresponding to a NP-complete or complete problem? Is there an established literature?
There's literature on how to write the Hamiltonian. I can't give you exactly the parameters. So most problems you can think of, you can encode as a ground state problem for a finite range Hamiltonian for some qubits of a certain dimension. And I don't know what the limits are. There's some, but the limits are below. But of course, this will not be a very simple Hamiltonian to study, and in particular, will have a very small gap. Because if you had a big gap, it would be easy to find its ground state. It's relatively easy. You could do some adiabatic cooling or something like this and find the ground state. It would give you the answer to your very difficult problem. So it's still a very difficult problem. And okay, you could hope maybe it should be considered as a question of quantum complexity, quantum computation complexity. And so maybe we have actually access to solution of problems and NP-complete problems. I don't know. But yes, the translation in principle has been done. People have proved you can encode basically every problem as a ground state problem. You're asking me more than I know for sure. So I can send you some references where you can read about that if you like.
Thank you.
So let's thank Bruno again.